bring close to surface and lead to the appearance of the central secondary structure. Such a line of the saddle is only possible at a constant admission of the demolished material. In hydrolocality is not supplied from the depth. It is exposed to destruction and sublimation, which was evident from the previous slide. Big hydrolocality structure is fundamentally different from terrestrial pingos, that it is not ice but crystal hydrates and the surface as a surface. Ice and clatratus may lie below. The burst of big hydrolocality takes place while closing of subpermafrost reservoir of pure waters and their growth in the process of increasing the thickness of the permafrost. The temperature of the freezing point of water must continually decline with the growth of its mineralization. Thus, it is assumed that in the Amazonian period, the Elysian plain was flooded and residual brines have survived to our time, at least locally. The main reason for choosing this place is plentiful water at the equator and an access to the youngest material from the depths with the aim of 4 traces of life. Water from the crystalline hydrates can be easily received and cleared of any salt by heating, sublimation, and reverse condensation in pure ice. Luckily, hydrates, salt, are magnesium and calcium perchlorate, Antarctica, and gypsum. Even the first step of spatial dehydration releases 16% of the water of this mineral. The volume of hedgehogs is 1 cubic kilometer. The volume of water-rich crystalline hydrates is 0.43 cubic kilometer, and water which is easy to extract is 0.073 cubic kilometer. This would ensure the colony of 10,000 people for a period of 500 years. For reason of isostasy, it can be assumed that liquid water below the level that mineralized liquid water below the level of the plain may lie deeper than 600 meters, and taking into account the thermal gradient is now accepted no deeper than 5 kilometers. Given the likely high mineralization of the residual stream, we can be more inclined to a depth of 30 kilometers. The prints are the additional source of water and magnesium, calcium, sodium, chlorine, bromine, iodine, lithium. If there is methane on Mars, it will be obtained from the big hydrolocality. Dune sand can be versatile building material that requires only a bonding agent. Dust is a good natural insulator for shelters. Both substrates are bought from outside and should contain iron, aluminium, silicon, titanium, magnesium. Thermal resources in the form of high pressure brine with a temperature of 25 degrees Celsius may be obtained from a depth of 6-8 kilometers. Thermal energy can be used by the heat pump. If life existed on Mars, it is likely it adapted and has not disappeared from the permafrost hydrosphere. Therefore, the search and study of life in the young water phases of big hydrolocality is no less effective than in the oldest fossils. The study of the material composition of big hydrolocality will indicate the mechanism of their formation and history of the permafrost in the vast field of Elysium Planitia. One can get the fresh material from the depths, which can give information about the presence of life. So-called low viscosity lava may give way to crystal hydrates. In my opinion, slope digs arise from the imbalance in the sublimation crevices when ice combines with salt. This phenomenon can be studied by the artificial initiation of the process on the slope of big hydrolocality in the appropriate season with the help of Rover. Dunes are an important element of the landscape and to be considered for the simulation of condensation of fresh ice. The negative factor of such cases is the dust. Difficulties with movement and picking can be overcome by straightening the upper layer of soil with mineralized water and at work sites and along the road. So it makes sense to study the slope peak substract by the dispatching the Rover 2020 there. My suggestion on this issue is in the NASA site 114 aeoli. Conclusion. For the first humanitarian mission and of the colony foundation, the areas with the active hydrolocality have advantages of equatorial plains are provided with large reservoirs of water and permission for the study of mineral resources and life in the depth of. Therefore, exploration of hydrolocality from orbit and by robotic mission is acute now. In particular, the important information of curiosity about hydrolocality Mount Shasta. Reference. Thank you for attention.
Thank you very much, Valery. I would like to remind you to stay online, please, until we have the question at the end. We'll have a group session with a question, so please stay online and we'll contact you again.
Меня было видно? А почему сейчас не слышно ничего?
Валерий, вас попросили оставаться на линии. В конце, после остальных докладов, возможно, будут вопросы и ответы.
Ага, значит, все было слышно, да?
Да, все было слышно. Все, спасибо.
Okay. The next speaker, 1046, Apollinaris Sulci. Who is that? Oh, Laura Kerber. I know she's here. Okay, wonderful. So this is a group, I'm actually co-author on this, but Laura Kerber is presenting, and without further ado, go ahead, Laura.
Okay, can you hear me? Okay.
Да, я слышу.
Hear a lot. Okay, so today I'm going to talk about Apollinaris Sulci, and it fits in right nicely with the presentations that have gone before. Here is a map of where we're talking about. So Gusev Crater is here. People have been talking about this. This is Apollinaris Mons, large volcano, and that fan that someone mentioned earlier, the Medusa Formation. The landing site is here. It's kind of this, we have this one giant sort of resource area, and our landing site is right to the south of it on this really nice flat plain. So we wanted a nice safe flat plain, and then we wanted a bunch of geologically interesting things, some of which have topography all around it. So I'll talk about the science ROIs first. First we have Deco Valley. So if you look, there's a context map of where we're talking about. This is right to the south of the landing site. We have this lovely sort of dendritic river channel, and it empties into Deco Crater, which is why I called this site Deco Valley. It's a well-preserved valley network. There's a potential for past habitability there and aqueous processes that we can study. Yardington, and I'll give this a lot of interest because this is also our big resource ROI, but this is essentially an enormous, they believe it's a volcanic ash deposit. It's maybe a mixture of volcanic ash, pyroclastic deposits perhaps, a redistributed aeolian material, and it stretches, it's got a volume of maybe a million cubic kilometers, and the spatial extent of this is about the size of the United States. And so here's just the edge of it. It's carved into these aeolian features called yardangs, which are wind-eroded ridges. So it's got diverse aeolian units, meteorological environments, and we've got this nice flat plain to land on. That's kind of a datable plane. And the interesting thing about this deposit is that it tends to preserve the things that it goes on top of. So we just heard about Zephyria planum. In Zephyria planum, there's a multitude of inverted river channels, actually, and they're much preserved in much finer detail than most of the valley networks in other places on Mars. I'll show you a little later another science ROI where more things are preserved. Sort of this layer is gently emplaced, and then it's eroded away. So we can kind of have a window into ancient Martian past. Here's a close-up of one of these yardangs. You can see, I hope you can see the sort of fine level layering that you can see in the yardangs. In other places along this kind of cliff of yardangs, you can see just meter scale layering inside these things. So we can kind of step back through the history of this time. Over here in this part of the section, we're sort of sitting on the dichotomy boundary. So we have Hesperian units, we have Noachian units. These are sort of classic Noachian valley networks. And so we can go and look at the time in Martian history when there's actually water flowing across the surface and ponding in lakes and rivers and stuff like that. It's really important for understanding the past. I call this one the Field of Dreams, sort of whimsically, because this is in Gusev. We were talking a little bit about this. You have the Columbia Hills, and you have lots of other kapukas inside Gusev Crater. So these geological units from older times sticking out among the Gusev basalts. And there have been people like Melissa Rice looking for additional sort of home plates. So places where you have maybe hydrothermal activity. A home plate's probably not the only one. It's an entire volcanic region surrounding this giant supervolcano of Apollinaris Mons. And so I thought, well, maybe there's lots of home plates. I see many kapukas, many home plate-like features. She's found a lot in the area. And so I call this the Field of Dreams, filled with home plates. So the plains of Gusev, this was brought up earlier with the wrinkle ridges. And this is a nice, well-constrained igneous unit from the Hesperian, datable plain. You can sort of tie that to your crater records. And we also know a lot about it because Spirit landed here, as we heard through the last discussions. And so we know that there's dust devils in the area, lots of atmospheric exchange. It's nice because there's dust devils in the area, there's little dust in the area, but we're not in a dust devil track. And the weather here is actually pretty nice. So we have Apollinaris Mons. I was talking about the huge volcanoes to the north of our EZ. And Apollinaris is another sort of big datable plane. It's got this huge fan coming out from it. And it's actually got it's hypothesized to have a magnetic anomaly associated with it. So if you did have a strong magnetic anomaly associated with Apollinaris Patera, in my mind I was thinking, well, that would be interesting scientifically. It might also be interesting if you had a finely tuned enough instrument, if you had a big magnetic thing just to the north of wherever you were living. So I call this Chaos Spectacularis. That's not its real name. We're often looking for chaos terrains because they're hypothesized to be indicative of sort of a water process, a water outburst. Maybe there was ice in the mesas, and then the ice sublimed, and then there's sort of collapse happening afterwards. So chaos is a thing that happens all over the place on Mars. So this would be a good keystone unit where you have a piece of chaos that you can look at, and then bring that out more broadly in the area. And these are true of a lot of these science ROIs. So you have a valley network that's representative of many valley networks. And you have the Medusa Formation, a piece of it representative of a formation that's, the size of the United States. And, Hesperian basaltic plains. All of these are sort of keystone units that you can go to the ground, take a look at, and then extrapolate more broadly to what's going on the rest of the surface. The Petrified Dunes, this is an area sort of way over here on the eastern part of the EZ. And this is an example of what I was talking about earlier, where the Medusa Formation tends to come over an area, it preserves whatever it's sitting on top of, and then at some point later in time, it unroofs that. And so that's very important. We saw at Curiosity landing site, the erosion of units sort of makes it so you have some units that haven't been exposed for that long. So maybe if you do have ancient organics or something like that, they're ruined if they're sitting on the surface for too long. But if you look at the edge of a unit that's eroding just so very slowly, maybe you can see something that hasn't been exposed for that long. I call this Sugarland Crater. That's not its real name, but you know, they have to be named after towns that have less than like 100,000 people, and I looked at Sugarland. Texas has like 83,000 people, so. And it's a nice name. So this is what happens when a crater hits into the Medusa Formation. It's a very fine-grained formation, so what ends up happening is you have a crater, and then you really preserve ejecta going out way beyond where ejecta is usually preserved on Mars. So these kind of rays extending out. And so this would be an interesting place to come and look. How does the impact cratering process work? It's not, we have fresh craters in the area. This is sort of an older crater, but it has elements that are preserved of the impact process well beyond what's preserved in other sorts of terrains. So now I want to talk about the resource ROIs. This is something that I photoshopped the other day. I photoshopped a city in England on top of my Yardangs, and then I took some launch sites from Russia, and I put them out here on the plane so you guys have an idea of what it would look like. And I've been telling everyone that they should just call one of these Yardangs for their own house. Okay, so general resources. We're near the equator. I won't claim that we're in the northern hemisphere. We're a little too far away for that. We're accessible in most Earth launch opportunities as a function of where we are. We'd be good for launching off the surface. These are all sort of things that are good in equatorial sites. Good for solar energy, panels, farming. In the place where we are, we have this sort of cliff of the Medusa Formation with all of its Yardangs that you just saw, but the big basaltic plain sitting in front of it is perfectly flat. So if you ever wanted to do something out there, build things, farm things, it's a nice place. Has a benign thermal environment, pretty low altitude. This is I'll show you the pressure at the surface, so certainly not the bottom of Valles Marineris, but not too bad. And so it's good for landing, pretty good for atmospheric related ISRU. This is the Medusa Formation. I wanted to show you the whole thing. So Gale Crater is right over here off the end of the map. It looks like there's a little Medusa Formation in there too. Here's the big Apollinaris patera. It's about 200 kilometers across. And we have this formation with a heart literally the size of Texas. And here's our landing site that's sort of right down at the southern part. So the Medusa Formation, what makes it an interesting resource? Well, it's a vast resource of fine-grained materials for civil engineering. That's the first part. We can tell by the way that it's continuously eroding and by its thermal inertia that it's fine-grained. But it has certain qualities about it that so it can hold a vertical slope, for example. It's not a crumbly material that falls down under its own weight. There's actually, it stays up in piles like kilometers high. And so you could use all of this fine-grained material for engineering roads, berms, landing pads, and then I'll talk about a potential resource for water and a structural resource next. So when I was looking at, the equatorial sites have a lot of advantages, and the big disadvantage of equatorial sites is the lack of ice, and so where are you going to get all your water from? That's a really important resource ISRU concern. And so if you look at, this is the neutron spectrometer map, or the gamma ray spectrometer map, you see that this area sort of stands out like a beacon, as was discussed earlier, as having a high, maybe up to 8% excess hydrogen, water equivalent hydrogen. And the other interesting thing about this area, so we don't have very good resolution here. We would say, what unit specifically has that elevated hydrogen signature? Is it the basaltic plains of Gusev? Is it the Medusa Formation? Could it be Apollinaris Mons? It's hard to tell because the resolution isn't good enough. If we look at the Medusa Formation with MARSIS and Charade radar, we get a really weird result that I thought was very weird because I study this area. It suggests either an anomalously low density material, like a dry material, even like way less dense than a pumice. And so you'd have to get like a reticulite for volcanologists. And you get this reticulite that's mostly air. It's like a foam. Okay. And then you you stack it up like 3 kilometers high. So how is that possible if, it should sort of self-collapse under the weight of its own self? But the other thing that it's also consistent with is ice, a high proportion of ice. And so when I looked at this area, it's near the equator. You're talking about neutrons, so you're only talking about this deep for the neutron data. So this says, okay, there's excess hydrogen here. Maybe that's in the form of hydrated minerals. But then the radar, looking kind of deeper down, says, well, it's either some very strange material that we don't know about yet, or there could be water ice hanging out there. So this is something where we can actually, you wouldn't go send a mission to this place based on this data. You'd have to say, that's kind of intriguing, but we need more data. So, and a big idea here is that here we have this resource, this fine-grained resource, all of these yardangs, these wind-eroded ridges, and most of the time we think of habitation being out here on the surface. But then you're exposed to radiation, and you're exposed to temperature extremes. Why don't you build your habitat into the side of these yardangs, essentially? Put this habitation inside this shelter. And so here's an example. I was in China recently, so here's a bunch of yardangs and what they might look like on the ground. Here's some people that actually already have built their house into the side of yardang. And if you zoom up close, you can see they have a satellite dish for communicating. And some brooms, I guess, to wipe away the dust. This is another example of an ash sheet that's in Cappadocia in Turkey. So back around the last millennium, in the year 1 AD or even before that, they were building huge cities into this ash deposit, subterranean cities that could shelter up to 20,000 people during times of war and their livestock. And they actually recently just found another city that was could house maybe 8,000 people. And the only reason they found it was someone was renovating their house, and they looked in the basement and they said, oh, here's a city, underground city that has 8,000 people that could stay there. So, and I wanted to show this. They used to have pigeons, and they'd use the pigeons for fertilizer, but they'd also use them to send messages between valleys. And I thought, well, we probably can't have pigeons in the yardangs on Mars, but maybe we could have a pigeon substitute. Send each other messages. So I wanted to show, this is the whole formation here. And you could have, so as you're exploring this whole area, okay, you have your main area, but if you wanted to send little caches to places and hide them from radiation for long periods of time, stores of material or food or whatever you wanted, you could have those sort of situated all over your exploration zone. Here's some caves, some little caves, the natural caves that I found in this formation, sort of nearby. And here's an example from, this is Iran. These are a bunch of yardangs. I wanted to kind of show what it would look like from the ground with all of these layers. These are a bunch of salts that you find often in regions like this. And here is an example of these yardangs in Iran. This is a truck, so you can see kind of how large they are. The ones on Mars are even more massively large. These are maybe 60 meters tall. So you can get an idea of what it'd be like to drive around in Yardang Town. So in the rubric, I was very conservative in my rubric. Most of the time, we have one of everything, but they're in different science ROI. So I can imagine different missions. Okay, this mission concentrating on the Noachian Valley networks. This mission is going to concentrate on the Hesperian. So each different mission kind of concentrates on a new area and learns new things. And I just put the resource ROI here because we essentially have one type of resource ROI that's extremely extensive. And so additional data that we might need, it would be nice to have more CRISM images over here. Sometimes they don't see very much. Even if there's a nanometer of dust, then it's difficult to see. It would be nice to have higher resolution neutron spectrometer data so we can distinguish which of these units actually has an elevated hydrogen signature. And then the big thing I wanted to say was that part of the Medusa Formation actually appears to sit at the top. This is a spectrally neutral unit that nobody kind of cares about because it's spectrally neutral, but I speak for the spectrally neutral because the spectrally neutral have no voice. And if we could go up there and actually see what the material properties are like, we have an asset on the surface that's close enough to do that. So that would be very tantalizing. And with that, I will finish. Thanks.
Great. Thank you, Laura. That's really intriguing. Some great visuals in there. The next speaker is 1043, also for Apollinaris sulci. And we'll just queue up the presentation here. Okay, Dr. Rice will present Gusev Crater, Apollinaris sulci.
All right, thank you. This talk is going to be a little different because when I saw Laura's abstract the other day, I noticed that our exploration zone is right on top of one another. Less than a half-degree difference from the center. And she's done a great job. And then that less than half-degree offset, Alex covered. Okay? So rather than have you hear the same thing over again, they both did a wonderful job, and I really wouldn't have much to elaborate on that. I kind of changed my talk around last minute, so if Ben and the rest of the organizing committee want to string me up, you got to catch me first. But okay, but anyway, so let me get into this. Whenever I talk about the Columbia Hills, which part of my exploration zone hit on, and Alex covered very nicely, I always like to remember who it's named after, the crew, STS-107. And these people, gave the ultimate for the sake of exploration. And space exploration is a dangerous business. We all know that. So I just always, whenever I talk about this, the Mars 2020 landing sites, I always put this slide in. Well, Spirit, we know exactly where it is. It better not have moved. And I'm the geology team leader on Spirit and Opportunity. And Spirit is sitting there between home plate and Tsiolkovsky Ridge, where it ceased existence or operational existence. And only thing I want to hit on with this is going back there, and Alex kind of touched on this, is if we go to this area, an extra incentive would be to visit the area, Spirit Rover. But it's got, besides cool pictures and the kind of history of it, it would have some practical benefits. Because by this time, it's going to be greater than 30 years of sitting on the Martian surface. It was an excellent long-duration exposure experiment. And this would be great. I've talked to some of the MER engineers a couple of years ago about some things we could look at if we went back there. And obviously what the Martian environment did to the rover in terms of its effect on materials degradation, like the solar arrays, wires and cabling, looking at our Cal target chips, did the batteries leak? A lot of things, practical benefits we could get out of that for using to determine and design and develop future not only robotic missions, but equipment for manned missions to Mars. And so it's a neat little thing. Now, this has been done before. If you're old enough, you remember this. Back in November of 1969, Apollo 12 landed right next door, about 600 feet away from Surveyor 3. It had been on the lunar surface about 2.5 years. Pete Conrad and Alan Bean went over there and clipped off the TV camera and some other parts, brought it back. So that was kind of the first long-duration exposure experiment ever done. You can see the lunar module sitting back there in the background there, Intrepid. The only other time we did this was LDEF with the shuttle era. And this was a long-duration exposure facility explicitly to look at, this is it right here being deployed by the remote manipulator system out of the cargo bay of the shuttle. Electronics, optics, thermal systems exposure. It was up there 5.7 years, a little longer than originally designed. And I guess you could argue right now, Stan, that the space station is one of these long-duration exposure facilities. So we've still got some things up there. But on Mars, Martian surface, we've got Spirit. We're going to have Curiosity. We've got the Viking landers, which we talked about earlier yesterday, and Spirit and Opportunity. So in the 2020 rover. But Spirit special to me along with Opportunity. But anyway, this was a slide that I had Joel Hagen, a space artist, put together for me for a Mars 2020 landing site meeting a little more than a year ago. And this is Spirit sitting here. That's the home plate. This is Von Braun Butte down here in Goddard Crater. Tsiolkovsky Ridge is up here. And this was kind of a depiction of the Mars 2020 rover coming to check out Spirit. This could have turned to a parking lot on Mars, I guess, if we go back there. So now, to go off topic, because like I said, Laura and Alex covered all the other science, ROIs, resources. And I kind of changed this around, and I'm going to go through this pretty quick because I know it's almost time for lunch, and there's one more speaker, and this is not on the agenda. But I'm a field geologist, and I've done a lot of field work and Mars analog environments with desert rats out of JSC. I spent some time in Antarctica I'll talk about later. And Stan alluded to this yesterday, and Antarctica's come up yesterday, so I kind of threw this in here. Now, the reason I put this in here is, it's about risk to crew. You want to reduce the risk to the crew. That's number one priority. So with field testing out in Mars analog environments, this will reduce that operational risk. It allows you to assess crew productivity. It's going to maximize your science return. This can provide training for your crews and mission developers. A little more detail about the risk reduction. Why is it risk reduction to do analog field work with the crews? Actually, this was done in the Apollo program, and that's really our only experience exploring another planetary surface. So I think Apollo, it's a long time ago. There's still direct lessons to be applied and learned there, though. This will ensure the crew can meet the challenge of doing science on Mars. In this case, it will allow you to develop your operations and procedures. That goes back into your safety. Technology development. You can't do this stuff in a lab. You need real slopes, rock, dust, all the nasty stuff out there in the field you got to deal with. And you're going to have to deal with on Mars. Also, it validate your command and control schematics and how this is all going to work. So this is all something that needs to be proved out and tested before you go there. So ultimately, it's all about reducing the risk to the flight crew and provide the mission developers and the crew a unique perspective of doing exploration. Any pre-mission activity without an analog site facility testing, in my opinion, is just going to be totally inadequate. You've got to get out there and get your hands dirty, so to speak. I'm a geologist, in case you couldn't tell. I've already mentioned that. Field work is an old saying, and I don't know who this goes back to. Hal Mazursky told me this a long time ago. The best geologist is the one that sees the most rocks. Very simple, very true. And field geology is contrary to a lot of what some engineers think I've encountered over the years. A field geologist does a lot more than wander aimlessly in the field, throwing rocks in his backpack and sipping beer. Now, we all like beer, but there's more to it than that, okay? Field geology, what you do, if you want to summarize that, it requires a constant iteration of what you see in the field, and it allows you to formulate and build and test hypotheses. And the only way you do this, you can't get it out of a book. You got to go out there and do it. So the experience comes with getting out there and doing field geology. When should, we're talking about sending astronauts to Mars. I've been talking about that a long time. I thought when I was in grad school I'd see it happening, and we're still talking about it. But I think the sooner you get the crews training with this in geology, because let's face it, one of the main reasons we want to Mars is to do field geology. Okay. Also, I know there's a lot of astrobiology, but I'm a geologist. Okay, so we're going there to do field geology, and at least one of those crew better be a geologist. Okay, and I think the Apollo 17 experience tells us a lot about that. But so you get the crew out there learning the art and skill of doing field geology, and like I said, you can only learn that by being out in the field doing it. You don't get it in a textbook. And if you do field geology, one of the things you probably know, it's a very humbling experience when you get to a new field site, because you get out there and scratch your head, you don't have a clue what's going on, but if you're persistent, you start figuring it out. And that's something you got to learn to do. Field geology is a cumulative science. And like I said, the more experience you get, the better you get. And you need to get the crew, the science operations people, and mission operations all working in conjunction to kind of get their mindset of doing this. This is going to be different than the shuttle or the station operations. This is exploration. It's something we haven't done since Apollo. This is just kind of fantasy thinking, but something I thought about years ago. If you're in a perfect world, what you could do is take astronauts, have them on, do an increment on the station, 6 to 8 months, to simulate a trip out to Mars, bring them back, check them out. If they're okay, take them down to Antarctica, place them down there. That's your Mars surface. They begin in an unknown site doing the work there. If you're really ambitious, after that's over, the crew could go back up on the station and simulate the rest of the time. Now I understand that's expenses and time and a lot of things. It's probably not going to happen, but it's just kind of something to think about. So Antarctica, 2 people come back from there, okay? I was told this before I went. You have the ones that love it and the ones that never want to see it again, okay? I loved it. That's why I'm going to talk about it some more. And I think Antarctica is a great place where we're going to do analog testing for sending people to Mars. This is a painting that was done back in the 80s. Chris McKay gave it to me. I can't recall who the guy that painted this, but this was based on some of the work they were doing in the ice-covered lakes and the dry valleys. And this is the analog of Antarctica, and this is the Mars thing, direct tie-ins there. So I think Antarctica is a gateway to human exploration of Mars. I spent 6 months down there in eastern Antarctica with the Russians at a place called the Bunger Hills Oasis. It's an ice-free area. So second largest ice-free area behind the dry valleys outside of McMurdo. And so there are certain traits, if you've been to Antarctica, you probably realize these, and it came up yesterday, and I think this is kind of important because this is going to be kind of something to do with the cruise. And I'm not an astronaut, Stan can talk about that. But some of these traits, I think, transition right over to the astronaut corps and also for doing Antarctic work. And in Antarctica, it's a physically remote, isolated environment. There's a lot of places no help's coming. Something goes wrong. That takes a certain mindset. You have to be persevere, flexible. You can read all this anyway. But these are some characteristics that any kind of field work. And I think when we're going to Mars, like I said, we're doing the ultimate field work when we go there. When I went down there, it was 6 months. It was me and one other American, the rest were Russians, went down on the Russian Icebreaker. But it was interesting because we had to make our last will and testament before we went. Now, people die in Antarctica every year. And when I was down there, a couple Russians were killed at a nearby base, a couple 100 miles away. So it's a real thing. And you had to agree that the Russian program, if you die, they bury you down there. They don't bring you home. The American program will bring you home. Well, we're with the Russians, okay, and we're basically living like Russians. And so we had to agree to be buried there. And the reason I put this in here, and this is a Chesley Bonestell painting of a burial on Mars, but when you walk by and see graves down there, it brings it home. And I was able to see several Soviet, at the time, bases in Antarctica. And they had a plane crash back in the late 70s. They're equivalent of DC-9. And there are 30 shallow graves sitting out there you're walking around. So it makes this stuff real to you. And that's something, we haven't had to deal with in terms of surface exploration on the moon or coming up with Mars, but that's something always hovering around out there. So we had about a month and a half going down the Icebreaker before we got dropped off of low physical activity, kind of, sort of like interplanetary cruise. And this is a picture of the helicopter when we left the Icebreaker, parked against the ice shelf. It was about 400 feet long, called the Academic Fedorov, and we did a 2.5-hour flight over the ice sheet before we got dropped off. And a Mil-8 helicopter, and I realize that slide isn't backwards with the nomenclature up there. But we slung all our gear we needed, and this lasted for about almost a day, bringing our gear, food, and everything. Because once they dropped us off, that ship went back to South America, and it was not coming to get us. We were there, okay? And when that last helicopter left, and you hear the rotor blades popping, I don't know, to me it was a cool feeling. It was neat. We're there, and nobody's coming to get you no matter what. And we were fortunate, nothing seriously happened. But, I'll tell you this, and I spent 106 days there, and that's very safe, like a walk in the park compared to going to Mars. And things go wrong. They will go wrong. And Stan alluded to this yesterday. It's not like, at 540 days on Mars, you can be doing science every day. The Apollo program was about a 30% rate. We were lucky here. I mean, it's about half, 50 days of doing dedicated geology of the 106. You can see other time was spent, when we landed, no one had been here in almost a decade, okay? This is a Russian base. It's very remote. And I didn't know at the time. We landed down here. A lot of these structures were destroyed. We had to rebuild the camp. And took about a month and a half. Then we have maintenance, all kind of things, clean, bathroom duty, all this nasty stuff you got to deal with, But down here, this is one of our track vehicles. We lost it, broke through the ice. We had 2 diesel generators. One of them went out the first month. I was there from the summer into the fall, so we were getting darkness. The last generator went out. Turned out to be our last night there. I could tell you stories about that, but I don't want to bore you. But the Russians have different ways of doing things. I'll put it that way. But we all got back in one piece. It worked. Anyway, this was an interesting day because we lost it. And if it had been a deeper lake, you'd have a different speaker here right now. We bottomed out right there. And that was the only one time in my life I ever had a beard. But anyway, so we did some scuba diving down there, East Frozen Lakes. That's just a series of images of me going down this dive tunnel, really what it is, in dry suit. And this is just a summary of what I just told you. It was 189 days total. It's the closest I'm ever going to get to going to Mars, unfortunately. But the last slide is kind of a neat slide because we're talking about revisiting areas. Like I said, this place we went to, no one had been there in a decade, and no one knew the condition it was going to be until we got down the ground. But there's a tradition in Antarctica putting signposts up Now, you can remember this is the Russian, it was a Polish base. The Poles abandoned their base, but there's signs, favorite places, your home, where you're from. Well, the Russian program is different because the last 3 weeks we had to be close to base. So if a helicopter shows up and it would be unannounced, you had to be out of there, okay? So we had to stay close. And like I said, the Russians have ways of doing things differently than us. But I was down making some signs, and I hear the rotor blades coming. So I run out of there, and we were gone within 45 minutes. Flash forward about 7 years down the road, another crew goes back down there, and I told the guy, it was in East Germany, from Germany, go down there and put my signs up and get a picture for me. So we did that. And he's got Phoenix. It's supposed to be Arizona, but there is a Phoenix, Alabama. I'm from Alabama. But so it's kind of weird how that worked out. So he's got, the mileage of his kilometers and some of these others. I'm from Tuscaloosa, Alabama, so he put that in there. And then I had him do Mars down here. So it was kind of cool. And I'm sorry if this went off topic, but like I said, I didn't want to repeat everything and give you a Groundhog Day experience. So I'm going to stop there.
Okay, thank you, Jim. That's incredibly useful information. I really like that statement. It makes it real. I've been up in the Arctic, and it is a different mindset when you're out there by yourself, and you make decisions differently. And I think that's kind of what you're getting at. Is you also everything becomes very clear. It's am I going to live or am I going to die? And that's the basis of your decisions, and it brings up clarity of mind that's just hard to describe, and I encourage everybody to go on a field trip like that if you get a chance. Next talk is 1012 Hebrus Vallis, and our speaker is Dirk Schulz-Mako.
A little bit butchered, but that's okay. I'm used to it. Thank you for having me, and I give the talk for our group. And as you see, it's we have a group of 6 people, and I'm the astrobiologist. So you have to have a little bit leeway with me on the Martian geology, although, we'll see. This is our exploration zone, and we wanted to be conservative to start with. We have actually a 50-kilometer radius, because even within the 50 kilometers we found so many sites that are interesting for us. There is, okay, that's how it works. We actually have here some sinkholes inside. So because our theme is access to the surface and to the subsurface, I think we are the only group who will actually put an emphasis on the subsurface. We have various fluvial features in our SOIs. There's one large crater there where we have crater uplift and crater ejecta. And our eyes, there's one also where the sinkholes are. And here, over here, with flat landing areas. Since we, as you will see in a bit, we're going subsurface, we do have sites where the fluvial sites also include potential for past habitability, clearly. But we also have potential for present habitability and refugia when we go into subsurface towards the caves. The potential for organic matter should be there as well. Noachian Hesperian rocks, we believe that there's also trapped atmospheric gases. Well, some of the things we are obviously not as sure, but we do have a range of Martian geologic time and datable surfaces, evidence of aqueous processes, there's no questions, really all of them fulfill that, and potential for interpreting relative ages as well, and a couple of the qualifiers as well. Here's one more time, Hebrus Vallis. This is a little bit larger. This is basically the area that you saw before. The field station would be over here on the flat surface. Here's a big crater. And then you have 2 distributaries, and one is ending over here in those pits over there. That is within the 50-kilometer exploration zone. And the larger area is actually within 50 to 100 kilometers of the station, So as it is defined right now, we could get there still as well too. And each of the two distributaries terminates within the isolated pit and trough networks, suggesting the drainage of flood waters into the subsurface, most of those areas. And the absence of evidence for ponding upstream of pits and troughs and the presence of channel pattern bars that extend into troughs are indicative of rapid and unobstructed flow into the subsurface, so similar to sinkholes on Earth. And that's what we basically believe that some of these features are. And we have of that one also a CMS infrared image, and you see over here there's a Vastitas borealis formation actually going through here, the boundary of the northern lowlands. And here also this kind of features that we see in this kind of image. So our science RI1 is where those pits were. Maybe let's go first. This is this area over here. Elevation is minus 3,680. There are multiple point access to the subsurface with a high preservation potential for evidence of past habitability and biosignatures. And so the question is really, how does the subsurface look there? Rodrigo et al. Alexis is actually one of our team members. He published a paper with some of us suggesting that high hydraulic pressure associated with mud volcanism formed pseudokarstic erosion along the feeder conduits. There's another interpretation by Carr and Mullen in 2000 suggesting a subsurface karst landscape by dissolution of buried carbonates. So there's obviously some uncertainty, but either way how you look at it, the inferred magnitude of floodwater infiltration points to the evidence of structurally stable caverns with permafrost having a mechanical strength of limestone at the average temperatures at Hebrus Valles, makes this still a very interesting and resource and science actually point of interest, because you do have those structurally stable caverns. And another point to realize is that obviously the Martian gravity is much lower than on Earth with 0.38 g. It allows for the caves to be about 2.5 times larger than the ones on Earth. And by our estimates, or by the estimates that were published in that paper, to up to 6 kilometers deep. So we could have really access to the very deep subsurface. And this is one of the places where we should then look for life, right? And extant life in those kind of cave environments. This is, for example, here Ice Cave in New Mexico. It's a very arid environment as well, but you have permanently ice in that cave. In the cave environments on Mars, obviously we don't know for sure, but we could have here permanent or transient ices as well, and secondary mineral formations. And on Earth, in some of the cave, you even find fish, right? We wouldn't find anything like this on Mars, but what we might find is something like this, snotites, right? That are microbial organisms that mediate mineral formation. So if we find something like this on Mars, we're already happy. We would have found extant life. So those caves are potentially long-term stable habitats, and they would preserve potential biosignatures as well. Science region of interest 2 would be one of the fluvial features here, indicative of aqueous processes and potential habitability. RI3, the same thing basically, is still kind of a little bit more intensive feature. All elevation between minus 3,000, minus 4,000. This is a little bit different feature, a big impact crater. And here we would have access to Hesperian subsurface materials with trapped gases, dating geological units, interpreting relatively ages, and we have here the primary impact, obviously, and some secondary impacts as well. LI6, again, the fluvial features, very convoluted, indicating aqueous processes and potential habitability. Let's look at the resource ROIs. The potential for ice or ice regolith mix is there in a lot of those sites. Also for hydrated minerals. How mineable that is or production is difficult to say at this point, so we're more unsure. Thresholds, 50 square kilometer region of flat and stable terrain with sparse rock distribution. There's actually multiple sites for that. One of them we used as our landing site. There's 1 to 10 kilometer length scale, smaller than 10 degrees. Within 5 kilometers of landing site. Again, we have multiple sites over here, and also for potential mining, and so there are multiple sites. Our I1, again, this is basically the same area, multiple point access to the subsurface, and here we have a high potential for water and as well as shelter. So we could imagine something like this, the exploration of a Martian cave or the subsurface. That can happen with the humans, with a little, look like a rover or tank-like thingy, or also robotic, or both ways. And these caves have several different advantages with these resources. They are protection from the radiation environment. That is incredibly important to have, aside from any kind of technological structure. Constant temperatures maintained by internal heat. That is a feature that we see in caves on Earth everywhere. And higher amounts of water vapor may actually allow liquid water to be present too, especially in the very low reaches of the caves. And even there's the vision of a human settlement on Mars by the Mars Foundation shows here that it will go, you want to go inside the rocks. So if you have caves already there, you don't have to construct the inlets and build them, but you just can use the rocks that are there already anyway. The caves that are there anyway. Okay. Our I2, this is clearly over here. We have a very nice flat and stable terrain near the landing sites, slope smaller than 5 degrees over most of the exploration zone, access to silicate minerals over the entire exploration zone, including sediments. We have low latitude, plenty of sunlight, and access to surface shelter. Regarding data needs, the single most important additional data set needed to access the science potential would be high-resolution mapping of the terrain and its composition. High-rise, Chrism, Omega, similar. This is important because it would be necessary to get a previous good understanding of landforms and surface composition to ensure high-quality science return. The single most important data set needed to assess the resource potential of the exploration zone would be probing the subsurface using radar measurements. That is something what we definitely want to have with the radar to see how far the caves go in to get a better idea of the caves and the subsurface. That should happen with high depth resolution with MRO Sherrod or similar. And obviously this is the highest priority for us because our site is basically based to have the caverns inside. And let me make a last pitch of the caves. As the first permanent human habitation on Earth was caves, if you don't remember anymore. That was a long time ago. And there are still pictures drawn onto the walls, and people ventured out and explored the surroundings. And that would be very similar happening on Mars, at least so we envision that. So whatever landing site would be chosen in the end, I think it would be really a shame if it would not have any caves with it. So a human field station should really utilize this great resource on Mars. Thank you.
Okay, so we're for the Q&A. We'll do it for 15 minutes so we can get everyone out for lunch. I don't mean to cut it short. I'm going to omit my questions, but I'll go ahead. Can we get everybody that presented up here? And Valerie, who is just? Can we see Valerie? And again, a reminder about our email address for people online. We've actually received a couple, but we work those questions offline. And so there. So we have Valerie. And let's see. I think we got it right. Yeah. Or is it? Okay, great. So can y'all all come in a little closer, just because we can make sure. Okay. You got it? Okay. So any questions? Yeah, right here. Do we need a mic here, please?
So it's true that obviously humans started having shelters in caves, but at that point in time they weren't worried about communicating with another civilization or planet. You guys, I think everybody talked about using the rocks as a shelter. Have you thought about how you're going to do the communication? Are you going to have like a base outside or on top of it, or what's your solution for that?
Okay, anyone want to take that?
Yeah, okay. Well, sure, it really has to be both. I mean, there has to be, like in the vision of the Mars Foundation, there has to be one part outside. I mean, you would want to grow plants outside as well, but one part can be inside, and you could grow even fungi and edible fungi and so inside. And a lot of lava tube caves, for example, have this ceiling windows often, yeah? So you could actually, in essence, you could put there a glass shield on it on the top and put a communication array on top of it too. So there are ways. But I think the main point is, so if you can go into the caves and you have additional shelter, you don't have to use anything constructed. You don't have to go in the space shuttle or whatever probe you have that gets you there, but you have additional shelter on Mars from radiation and everything. And this, I think, is really useful to have.
Any other questions?
Yeah, I wanted to add that, yeah, for our particular thing, you know, for his, it's like there's a whole plane that you can put your communication devices on, and then you can go into the cavern. And for us, it's you could either put it on top or you could put it out in the plane. And so you sort of have a safe place to go where the temperature is always around the same amount and there's not so much radiation. And then you have your working area that's sort of out where you want to go explore. So, because I think there's a lot of nice places on Mars to visit, but there might not be that many nice places to live. So, these examples might be a nice place to live.
Here, Jimmy.
No, those are cave dwellers.
Okay. Okay, right here.
Dirk, there's some thinking that some of the landforms that we associate with fluvial channels on Mars may be volcanic in origin. How would a volcanic interpretation for your caves change their astrobiological value versus a thermokarst cave? And then a follow-up for Laura. What do you think made the caves in the Medusa Formation?
Yes, I'm here. Okay.
Y'all are hot mic, so can you make sure you're not talking over the loop? Okay. All right, go ahead, sorry.
All right. I think it wouldn't, from the astrobiological potential, probably would not change it much. If it's volcanic, if it's lava tube caves, you have some more advantages that are even more stable than that. They may go about the same distance in, actually, as if it is permafrost cave or if it's limestone caves. I mean, limestone caves would be probably the highest astrobiology potential, but I mean, I think that is relatively unlikely, not impossible, but that's why we need to know more. But in either way, it would have a high astrobiology potential. And
Oh yeah, so the other question being where the caves that I showed. So I showed a couple caves. I've only found a few, and I've looked a lot of places. And so I think in those cases, I don't know how deep that cave I showed. One of them looked like it was just an alcove, and the other one was probably a little bit deeper of a cave. So I could imagine those could be formed through aeolian processes, or if in this particular region there was some jointing, you could have aeolian plus just collapse of, a top layer or whatever. I think the interesting thing about the deposit is its material properties, that you can erode it, obviously, but it forms yardangs that have steep walls. And that's kind of what you're looking for if you want a place that holds a nice cave. I don't think you'd find that many natural caves, just because most of the ones on the Earth, has to be some water involved. And I don't think there was a lot of water in this area. It doesn't look like morphologically that there was. And so, I think you would really want to go up to it kind of and test its properties. And even if we could get more charade tracks across it and sort of see if there's a variety in its material properties based on its dielectric constant, then you could sort of see which areas were the most ideal.
Okay. Anyone else? Okay, over here.
All right, comment on the caves as it relates to actually the exploration of them. While the caves may be a more isothermal environment compared to the surface, as was already mentioned, the amount of energy that is expended to heat the mobility actuators on Curiosity driving at peak insulation during the day is not inconsequential. The caves may lead to systems that we cannot operate for thermal reasons due to the fact that you don't have any sort of heating coming in from insulation. Another comment along those lines is civil engineering in the yardangs or the caves. Is it worth the risk that a collapse may take out your key piece of civil engineering robotic systems, as opposed to having something on a surface that may be able to manipulate, but a smaller failure would not completely destroy that capability?
Well, even if it's a permafrost cave, at the temperatures that we have, the rigidity or the structural capability would be like a limestone cave on Earth. So and if you have a lava tube cave, it would be even more stable. So obviously would have to check that through first where you go inside and place your valuable equipment. Caves we would expect that they have higher temperature than the outside on Mars, because there would be some heating from below. So in that way, I think it would be still well worth a slight risk, yeah.
Okay, and Jim, no, let's get that mic up here, another mic, because we need this mic here. Okay, oh, yeah. And Valery, this is a question for Valery coming up.
Valery, can you briefly review your information about the thickness of the cover on top of the ice?
She's not hot because I'm a mic on this thing. No, we can't hear you. Okay.
Do you want me to repeat it?
Yeah.
Repeat?
Oh, wait 1 sec. Let's make sure he can hear her. Yep, here, take this one.
Да, теперь слышно четко.
Okay, Jim, go ahead.
Yes,
Да, пожалуйста.
Valery, can you briefly describe the thickness of the debris on top of the ice in your model?
Да.
Да.
Сейчас. Значит, наслоение имеется в виду тела гидролокалита.
Yes, the thickness of the debris on top of the ice.
Come on down. Just come on down. I think it'll be easier for you to hear John that way.
Над льдом, значит, над льдом находятся кристаллогидраты, и они укрывают от сублимации. Толщина их сейчас трудно сказать какова. Я думаю, что несколько десятков метров.
It would be difficult for me to assess the thickness of the debris on top of the ice right now, but I estimate a few tens of meters.
Okay. Спасибо.
Okay. Great, thanks. All right, next question. Do we have another question here? Right here. Hey, can we get...
In Idaho, there's a huge basalt field, Valley of the Moon, I think it's called. It's a huge... Yeah, Craters of the Moon, there you go. You're familiar with it, good. Maybe they already have the answer. There's lots of lava tubes there. One of the things they stress as the paths that you go through there is absolutely do not enter those because it is dangerous. Then those things do collapse all the time. Now, it may depend on how much material is over it, how deep it goes, what the structure is, but that is one of the things that they do stress. What's your comment on that?
And
Okay, hang on, let's get on.
Hey, we found, if that,
and I think
hope that's not a problem on Mars.
Well, I was thinking just to say one thing about the collapse. If you were supposedly building something in there, we have all sorts of construction techniques that we've been pioneering for building out on a plane, and then we have this idea that we'll cover them with regolith or something. So I can imagine it would most probably be a hybrid approach where you'd put whatever you're putting in the cave, but you have some kind of additive construction, or you have some, way to make sure that it's not going to collapse. You might have like an inflatable shell, but it could have like ribs or something. I think there's a lot of ways you could go to reinforce and make sure that your main, maybe your exploration caves you could go into, but your main caves that you need for survival would be reinforced, I think.
Okay, I think Dirk has one thing he wants to add to that.
One of the very last slides. The second last one. This is a lava tube. This one, I wanted to show. That is Ape Cave, that's in Washington State, just right next to it. And there's thousands and thousands of people walking basically all the time through. And that goes very deep inside. And it's absolutely safe. And there's no rattlesnakes either.
There's also a slab of lava fall right there.
Okay, but that would be okay. All right, that is the wrong image. This is another. That's the cave has no lava. Yeah. Okay, you want to avoid the lava. Okay.
All right,
I have
hang
the
on,
microphone over here
second,
too.
One second. Okay, I think Carol back here.
You actually have identified caves in Dirk's the presentation that Dirk gave, but you could clarify that. Inferential evidence is not probably practically sufficient, but I must say, having been in some caves myself, they are extremely dangerous places. They are very three-dimensional. They have natural caves. Usually you have to be doing a lot of stuff on rope. Not having natural light is a very significant problem. And the temperature that you're going to be at inside the cave is going to be the mean annual temperature, which is going to be cold, unless it is a very deep cave and therefore getting significant internal heat.
Any comments to that?
Yeah, I mean, it still will be challenging, that's no question, but it's much less work than if you would have to dig basically yourself, and if you already have a cave. And I mean, in principle, yes, those points are inferred. There are some geological marker with the pits and stuff, what I explain, where the water must have gone. And but what we would really want to have before is some kind of a mission that uses radar. The best would be ground penetrating radar, to have it on the surface to really fix it down. What are the cavities down there, and how deep do they go? And I mean, I think that would be stable on Mars, but obviously we want to make sure too before we put people in it.
Okay, and Jerry back there, I know.
Yeah, I wanted to make a comment for all the teams so far with respect to the resource ROIs that have been identified, and as you develop these sites, and that is pretty much what I've seen so far is a kind of a check mark. Yes, the resource is there or not. But however, that's step one. To a certain extent, the homogeneity or heterogeneity of the resource, the concentration, the distribution, how can you get to it? So, for example, if it's on a slope of 40 degrees or 30 degrees compared to a flat surface, how far away it is from your habitat. All those things factor into it. So when I see an ROI for ISRU that's 100 kilometers away and nobody has talked about the path of getting there back and forth, that kind of thing needs to be taken into consideration. And so I would recommend that when you're going through what measurements are needed, both from existing assets as well as others, that you take that into consideration. And when you start talking about caves and theoretical water deposits there, what do you really need to do to verify or disprove those concepts? Because we're not going to pick a landing site based on, there might be water there and not, something else. So those kind of discussions need to be considered by the teams that I haven't really seen yet.
Okay, and in all fairness, it's starting the process, as you know. So any comments y'all want to make?
I just thought it was really quite interesting because I was working a little bit with the ICE working group and then with the ISRU, and then having some ISRU people on my team. And so those sorts of things came up. And in our situation, you could say, okay, if the water is here, then this is how we might be able to get it out. But we realized together that we just didn't have enough information to pinpoint exactly where that was. And so I think having that sort of back and forth interaction was very critical for us, and I think critical moving forward, that ISRU people being embedded and scientists being embedded, and them being able to say, this is the information we need, and me saying, well, I don't have that information, let's figure out how to get it. I think that's a great point.
Well, yeah, sure.
I think Laura captured that very well in terms of once you tell us there's water there, we'll go and get it and mine it and do all that, but we need to have confirmation that exists.
So we are out of time for questions. I would just like to maybe echo what Laura said there, which is that part of this, as Jim alluded to, is building the community. So one of the things I would say for everybody that's proposing exploration zones is really be thinking about what other talent you need on your teams, that brings that knowledge to bear, so we can really start building even more integrated proposals. Because that's really what this is about fundamentally. So I just throw that idea out as maybe a concluding thing for this group of sessions this morning. We are going to end now. We need everybody back here a little before 2 o'clock because we're going to start at 2 sharp. So thank you so much. Thank you guys too.